So welcome to session 10. So three more sessions. So we will be taking our extra session on April. Okay. So you people will receive mail who have registered for this course. Okay. So I guess it's on April 12th or April 13th, and it's on Tuesday. Yeah, it's on Tuesday, and so it will be at 2 p.m. on the afternoon. So yeah, in previous sessions we have discussed about different extractions process for our different types of metals, right? We have discussed for copper more extensively. Right? We have discussed how the copper will be made. So, and then yeah, so in copper we have discussed. Okay. Yeah. Sulfide, or you can call it as a cuprate chalcopyrite, and then we did the fourth rotation process for sulfide ores. We do the fourth rotation, and then we went to after fourth rotation, then we went to roasting process, right? So partial roasting, not complete roasting, as we have discussed before. Why we do partial roasting? So that not everything converts into oxides. So when oxide smelting is a bit tricky because oxides have very high melting point, so we do not go to that. And when we do for complete roasting, then the slag will pick up every oxide, so again, which is not suitable. So we do the dead roasting part, where we want to remove as much as iron oxide as possible, and also to remove the volatile matter. The first initial thing is to remove the volatile matter. Then we went for smelting process, and then that smelt matter is used for the converting process, where in converting you will go through three different stages. First we do the slag making process, where you remove the iron oxide as much as possible. Then you go for the converting, where you convert whatever the copper sulfide, you start doing oxidation, and copper sulfide will react with copper oxide to give you copper metal, right? So yeah, and after that we have discussed a different process to extraction. How do we extract lead and zinc, right? So yeah, we can extract both lead and zinc at the same price. At the same time. That is called the imperial smelting process. We have also discussed that, and we have discussed how to extract alkali metals also. Not a bit specific, but yeah, we did discuss. Now, coming in this session, we will discuss on the reduction of iron oxides, or the extraction of Fe from iron oxides, or the hematite. Right? The most common ore we see is hematite ore. So before going to the extraction, we need to know which is the best reducing agent. Again, whatever we see from the most of the ores we get are in oxide form, or they can be in some carbonate forms or some fluoride forms, right? So mostly we deal with either sulfides, oxides. Okay. So iron is mostly available in oxide form as a hematite ore, Fe2O3. So we need to reduce that to get elemental Fe. And the best reducing agent that has been used from the past ages, like even from the decade, right, few decades, we still use the carbon coke. Coal, people used to use coal, but now due to the very many advancements, now we are using coke. And the best where we find the reduction of iron is in the blast furnace, right? So blast coming from the hot air that we blast it with to the ore, or mixture of ore, or you can flux or coke. Okay. So that's how you get the name blast furnace. So iron doesn't reduce in a single step, right? So it undergoes multiple steps. So first you will have Fe2O3, which will undergo the reduction to form Fe3O4, and which again will undergo reduction to form FeO, and finally you have, this is called as hematite. This is called as hematite, and this is called as a magnetite because of its magnetic properties when compared to all the other things. And FeO is called as a wustite, and then finally you have elemental iron or ferrous form. So this is the reduction cycle of Fe2O3. We can reduce with any reducing agents such as carbon and hydrogen. Okay, so carbon can be coming from coke, and when you burn the coke via blast air, you oxidize it, which will result in the formation of carbon dioxide or carbon monoxide depending upon the temperature. Okay, so let's say degree centigrade, it will give you carbon monoxide, and this is called again called as a Goddard reaction or gasification reaction. Why? Because the solid is being converted into a gas, right? And this carbon monoxide is highly reducing agent, and it can reduce your Fe2O3, right? It can reduce your Fe2O3 to FeO or Fe3O4 because that is the second stage, right? And getting carbon dioxide. So this is your solid, this is your gas, this is your solid, this is your gas. Now this has a negative enthalpy, that means it is an exothermic, but the reduction of Fe3O4 with CO is not exothermic, it is an endothermic process. And again the FeO reacting with CO to give Fe, again this is an exothermic process. So overall reaction, if you see, it will become your exothermic process, right? So yeah, so that's how the reaction happens. Now, yeah, so this is Fe2O3 to Fe3O4 and FeO. Now, coming to the iron making in blast furnace. So, blast furnace is a vertical furnace which is of a certain height. Okay, it's not like very small one. So, what exactly happens in blast furnace? So you see in blast furnace there is both the reduction because you are using the alternate layers of coke and your ore, right? So if I draw, I'm just only drawing the cross section, okay? I'm not drawing the full thing. Now you will find layers of, okay? I'm just using schematic, okay? I'm not like it's an actual way. This length may vary depending upon the type of blast furnace and the height of the blast furnace that we are trying to use. So typically the height of the blast furnace lies between, you can say, 25 to 30 meters depending upon which company is trying to make it. Okay, so you will find this alternate layers. At first, let's say this layer is my coke layer and this layer is my pellets or sinters that we are trying to use. Okay, yeah, they can be ranging from 10 to 20 mm. Pellets are more, see again I will explain the difference. The pellets, what is the difference between pellets and sinters and briquettes? Okay, so pellets are mostly, you will find most regular, or you can say it is more technically engineered when compared to your sinter. So pellet is your having a defined shape like circular or spherical type, and which is a consistence of your ore, flux, coke, and some binders to hold these things together. And then you heat it to 1000 to 1200 degrees centigrade so that it becomes hardened. And then pellets have good porosity because this, whatever the binders you are using, they are trying to escape and they become porous. Okay. So it is very good porous. It has very good porosity when compared to your sinter and pellets. Sinter is nothing but it's an irregular porous mass, but it's formed via fusing different things. Okay. So for example, you are fusing your iron ore and flux and coke. So it is porous but not as porous as your pellet, and also it is very much in irregular shape because you are not defining anything because you are trying to just fuse, right? Fusing happens irregular. So and then you crush it and make a fines. That's how the sinter works. And briquetting is nothing but you are creating in a different shape like bricks. So you can say like it's a rectangular shapes you want to try, and they have very much less porosity when compared to your ores and sinters and pellets. Okay, so all three processes are same. You are you have very fines. You are making them into a certain size by compacting them. Okay, so that's what about pellets and sinters. And pellets are more engineered when compared to your sinters. So pellet making is a bit you can say processful when compared to your sinters. Okay, now that is all about them. So yeah, here in this layer you can use either your pellets or maybe you can use pellets or you can use sinters, right? So that's about them. And then yeah, and from the tubers you have your tubers here, okay? Because it is a circular tubers, so it is surrounding your blast furnace, from which you blast heat hot air, and that air contains your oxygen, and this oxygen will react with your carbon to give you carbon dioxide. And again at those temperatures, because this is an exothermic process, right? So at that temperature this carbon dioxide will again react with carbon to give you carbon monoxide, right? So this is about that. Yeah, so we use naturally preheated air. You can say it is heated up to greater than 1000 degrees centigrade, okay? So yeah, it is a blast of air, so it is at higher atmosphere when compared to your that. And also if you use if you purge at 1 atmosphere, and because the load is so much, your pressure will decrease. Whatever the gases will come out, they cannot be taken out very easily, right? So some gases may remain trapped because of the pressure difference, because you need to have some pressure difference for that, so that the gas can flow from here to here. Okay, we know that hot air actually tries to move upward because of the density difference, but still you need to have some pressure difference so that the gas can move upward, right? Yeah. Um, yeah, and there are different regions. So there is stalk, there is a belly, there is a hearth, there are different, right? And this heat can this temperature here can go up to you can call it as adiabatic temperature, adiabatic flame temperature. See, again the flame temperature is nothing, so sometimes we use in terms of combustion, the flame temperature is nothing but what is the maximum temperature with which your gases, the product gases, are coming out of the raceway. Okay, so for example, this is my combustion zone. I'm trying to combust my air, let's say my fuel and air, and here it is the combustion, and then you're trying to like throw the byproducts, right? We do not want to store them. So let's say the products are coming out, and at here what is the maximum temperature they can achieve product gases at your raceway. Raceway is nothing but from where the product gases comes out, and the same goes for here also. The adiabatic flame temperature, when you try to burn your air with because this is a combustion reaction, right? So you are burning your coke with your oxygen, right? So that means you are creating indirectly a flame, so that you are indirectly creating a flame or gases combustion. So, and the maximum temperature these gases can take is up to like 1950 degrees centigrade, like greater than 1950 degrees centigrade. Okay, so depending upon the type of air you are trying to use, okay, whether it is enriched air or enriched oxygen air. Yeah, so again there are different what should I say, there are different regions. Okay, so let's draw our and people may ask why there is this increase in the size, right? Why not keep it like a single cylinder, right? Just like, why cannot the blast furnace can be like this? Why it should be a tapered outward and then inward, right? The simple explanation is, when you go from Fe2O3 to Fe3O4, there is this increase in volume. Okay, so whenever Fe2O3 goes undergoes reduction to Fe3O4, there is increase in volume. There is a drastic increase in volume. The same goes for this also. So that's why, to accommodate that volume expansion, you need to taper your blast furnace. Okay, and again from FeO to Fe, when you go to metallic iron, again the volume decreases again. So that's why you again tap it back. So that's why this tap in and tap out thing you see in the blast furnace instead of vertical straight cylinder, right? So at first you will have a stock line. There is a head from where there are different types of how can I say charging. There is a bellless type charging. We are not going deep into the iron making technology, because there are different courses for that. So you can have one lecture just on your charging of iron ore and coke itself, because that's how that much technology has been evolved for the past few decades, you know. So there are different types of charging: bell-less charging, with bell charging. Okay, there are this rotation type charging. Yeah, there are different types, right? And these are all based upon the efficiency. So the best efficient one will be used. So these are all on different types of trials and errors and so many simulations. Okay, they are not that much straightforward. Yeah, once you get the actual results, then it will become straightforward. Right? So yeah, this is your stock line, and then you have your stack. This is your stack. This is your belly, and this is your hearth. Hearth is where you collect your how should I say, the carbon. So this is the Tours region. So from Tours region, whenever you try to purge the gas tries to move like this, right? This is how it tries to move. Right? So because of this, here you have a very active zone. Active zone is nothing but your air, whatever you're trying to purge, the air is continuously reacting with your how should I say, reacting with your coke. So this is called as an active zone. So continuously reacting with your air to produce carbon dioxide, and carbon dioxide can react with carbon to carbon monoxide. So whatever is going to get here will get reduced, and then you have this cohesive zone. Cohesive zone, because of the temperature rise. See, when you are going from bottom to top, because the temperature, as I said before, the adiabatic flame temperature reaches 1950 degrees centigrade, and so that's why the temperature goes down when you move from bottom to top, right? And because the temperature is very high, so this, whatever the iron that has been remained, which will become a cohesive. That means it will become soft. Okay, you will have a contraction also, so that's why you call them a cohesive zone. And there is this called as a dead zone here, this region. Why? Because the air is not like available for combustion here, and the best part is this, whatever the coke that is been here, it just floats on your slag and liquid metal, right? So this is actually a very beautiful thing when you actually sorry, you cannot see the how the blast furnace actually happens. People have tried, they had made a miniature blast furnace. They tried to quench the whole miniature blast furnace and see what are the different phases and what are the different things happening inside a blast furnace. And people have actually tried. They made a miniature blast furnace, and then they tried to quench everything in liquid nitrogen to see what exactly is happening inside. What are the different stages, phases? What are the different places that you can find different types of phases, right? So the top region is mostly your granular region, because the only thing that you find will be reduction. That's all. There is nothing else. Okay. Now, and why these names have been given? In granular zone, you mostly have charging, mostly drying, preheating, or you can say, because whatever the gases that are coming from bottom to top, because the gases are very, they have very high temperature. That means the adiabatic flame temperature is large. So they try to pass their heat energy to the iron ores and coke layers that are being coming from top. Okay? Yeah, and then in this granular zone, you can find this reaction very often. So everything happens here, most of the reactions. Okay. I'm not going to balance, right? So please bear in mind. So, and again, the FeO will react with your CO to give Fe plus CO2, and because the temperature is still high, so whatever the carbon dioxide that has been formed, again will react with coke to give you carbon monoxide. Okay, so this most of the FeO you will find being, some of the FeO you will find being reduced here, and in cohesive zone, yeah, whatever the iron oxide that has been left will instantly react with your carbon monoxide and will give you carbon dioxide. Again, the same reaction happens here. The Goudot reaction, gasification reaction happens. So in cohesive zone, they become the contraction happens because oxide has been taken out. And in active coke metal zone, see, these are all indirect reactions. Indirect reactions is nothing but these are the solid gas reactions, right? And in active zone, you can find gas metal reactions and metal reactions also. That means the coke is directly reacting with your iron, which is again endothermic process. So um, right. So sorry, not another one again, which is slow. See, whenever there is a metal type of interaction, metal type of interactions is very low because the contact area is very less. And when you go to gas solid reactions, because the gas has more volume when compared to solid, and the solid particles are completely covered with gas. Most of the places are covered with gas, and so because of that, you have more surface area for the reaction to happen. Right. So these are the different reactions happen. And stagnant zone, you have because of coke standing on your slag and should I say your uh, liquid metal. See, whatever the iron, because of the coke standing there, right, there is a dead man zone, right? Let's say this is my earth, this is my slag, and this is my liquid metal. So whatever the iron, because of the temperature, so this is my stagnant zone, right? Whatever the iron that has become melted because of temperature is very high, this melted liquid droplets will trickle down through the coke and will go into your slag, and then slag to your liquid metal. And when they try to trickle down to this coke, they pick up carbon. So that's why the pig iron contains more than 6 weight percent of carbon. And where this 6 weight percent of carbon is coming from? Because of this trickling down thing. Right. So, and you have phosphorus pentoxide, other thing going, right? And yeah, these are the different types of impurities that you will find. No. And also carbon, because it is getting saturated, and because these are very highly reducing atmospheres, right? The carbon monoxide and the temperature that we are trying to use. So because of this highly reducing atmospheres, you will see the pickup or the reducing of these metal oxides also. Right. So okay, so let's now talk about mostly about the impurities, how the impurities are being picked up. So you will have manganese, phosphorus, silicon, and sulfur. Right. So you will find these things, and again sulfur. To remove the sulfur, you need oxidizing conditions, but because of reducing conditions, again you will end up with sulfur. You can control the amount of being picked up by adjusting your basicity of slag. Okay, so basicity is nothing but we are trying to add calcium oxides. So basicity is nothing but the oxides which can donate oxygen atoms, right? So yeah, so adjusting basicity of slag, and again the temperature. So let's say the phosphorus pentoxide that is present in solid will be reduced by the coke to give you phosphorus, so, and carbon monoxide, right? And the same goes for manganese oxide. You have your manganese in the melt, and the same goes for silica, carbon reacting to give silicon plus carbon monoxide. At that temperature you will only find carbon monoxide, no carbon dioxide, because the moment the carbon dioxide forms, it will again react with coke and give you carbon monoxide. Okay, so above 800 degrees centigrade you will mostly find carbon monoxide, no carbon dioxide. Carbon dioxide is not stable at that temperature. Okay. Now, and yeah, when you with increasing temperature, these things will get more probable. I mean, you are making sure the reaction move forward. So because when you see the delta G naught values, it's mostly in the form of A minus BT. So higher the temperature, higher this product will dominate, and higher the product domination, more will be the delta G naught value. Okay, so that is one point. And again the basicity. See, when you will find iron sulfide, right? And when you add calcium oxide, so this calcium will take out the calcium sulfide, and you will end up with FeO. And this FeO will again react with your carbon to give iron, right? So this is one thing. And again when you so let's write let's talk about the silica. So when you try to write the equation for this guy, it's a carbon, right? It's not two. Now, when you try to decrease the activity of silica in the basic slag, so this will become positive, right? So if I try to decrease this thing, then what's going to happen? This will move backward. So whatever the for the forward reaction, it is not possible. Then the delta G will be more positive. So that's what happens here. Now all the phosphorus that has been present, even if you tried, even if you do anything, because the carbon, yeah, we are maintaining very highly reducing atmospheres. We need oxidizing atmosphere so that the phosphorus pentoxide can be taken out. Okay, and this phosphorus pentoxide is easily reduced by the carbon and be picked up by your iron. So you cannot do much about that. And the same goes for manganese oxide. Manganese oxide has the same characteristics of as Fe2O3 or other iron oxides that are being reduced. So again being basic oxide, it cannot picked up by your again basic fluxing agent, right? Basic oxide. So again that is one thing. So yeah, again you will find manganese to be in your um, liquid melt. Okay, you will find the importance of this guy in basic oxygen furnace. And when you in basic oxygen furnace in the refining process, which we will talk in a bit. So yeah, we'll come to that in later, because let's complete this iron making. Okay. And the next guy which is going to pick up is sulfur. So again the sulfur transfer from metal to slag, right? From metal you have metal and you have slag. So you see the calcium sulfide will form slag, right? So you have iron sulfide in a metallic form, and this is your slag fluxing agent. This is your form slag, and this is your FeO. And this reaction highly depends upon temperature. Higher the temperature, easy for this guy to pick up, right? And again, because as I said before, maybe I said wrong. Sulfur needs your reducing atmospheres, right? Because oxygen and sulfur belongs to same family. They need reducing atmospheres, and because you have reducing atmospheres here, carbon dioxide, so this sulfur can be easily removed here, right? So yeah, it's better to reduce taken out from this blast furnace instead of your steel making. Okay? And after this, you will have the steel making process, right? So this is what we see in the blast furnace. Now again, there are different things that has been updated. For example, people are trying to use more metallurgical grade coke, so that again why do we use coal not coke? Oh, sorry, why do we use coke not coal? Coal has less burden capabilities, and see there is whenever some particles are going down from top to bottom, and there is a friction between them and also the walls. Because of this, there is much of the erosion happening, and coke has much erosional strength when compared to your coal, and coal has many impurities which we do not want to deal with when we are trying to do the smelting process, right? And the reduction of iron. So we try to remove those volatile matter by doing the destructive distillation, which I have studied when we are trying to learn the coking process, right? Where we have vertical retorts and the batch-wise process happens. So we do the indirect heating. We do not want to burn the coal because it will again become carbon dioxide, which is not suitable for us. So we convert it by indirect heating to give us coke, right? And again, people have tried to do the oxygen enrichment, right? The oxygen enrichment. That means whatever the blast air that you are trying to purge, increase the oxygen content in it. Right? So when you try to increase the oxygen enrichment, the gas volume will decrease first of all, and because of this, the amount of heat transfer will also decrease. So if this decreases the again there are two types of we have discussed, right? There is this indirect reduction which happens at the top, and there is a direct reduction which mostly happens at the bottom or the above earth. Indirect heating, indirect reduction. Sorry, direct reduction and the direct reduction. You need both indirect and direct reduction. Why? Because direct reduction is exothermic. Indirect reduction is it takes energy when compared to direct reduction. So if you do not have a direct reduction, then everything will cool down. Again, you cannot have a hot metal from the bottom. And if you only have an direct reduction, then again there is a huge use of coke there, because see, whenever we do direct reduction, we use this formula. Okay? And when we talk about indirect reduction, we talk about carbon monoxide. See, the difference you can see, when one coke is reacting with the carbon dioxide, it will give you 2 moles of CO. You can see 1 mole of coke is giving you 2 moles of carbon monoxide, and 1 mole of carbon monoxide is giving you 1 mole of iron. Here same 1 mole of coke. Now you can see, for 1 mole of coke will give you 2 moles of carbon monoxide. So half of carbon monoxide is extra is being used to give you 1 mole of same amount of elemental iron, right? So that's why we call this as more coke costly when compared to this, and this is just the balancing equation. You can easily have do understand if you try to balance this equation, and it is simple. See, 1 mole of iron oxide is giving you 1 mole of metallic iron. 1 mole of iron oxide is giving you 1 mole of metallic iron. But the difference, it is using 1 mole of coke, but here it is using 1 mole of carbon monoxide. So there is still half mole of coke is left behind for the further reactions, for the further reduction of iron, right? So yeah, that's why this is coke expensive, but not this guy. But this guy needs heat energy, but this guy doesn't need a heat energy. So that's why it is a trade-off between your direct reduction and indirect reduction. So that's why the best thing to have is, if you have 3 parts or 4 parts, the 3 parts is being taken by indirect reduction, 1 part is doing direct reduction, or it is 2 parts, I guess. So total reduction of, there is a total reduction of, if you go, 2 parts should be taken by indirect and 1 part should be taken by direct reduction. That's how the heat balance can be maintained. Okay, so yeah, so that's why there is a limit to which you can use the oxygen also. So the maximum the limits for oxygen enrichment is below 9%. Okay, so yeah. Again, increase in the top pressure of a blast furnace gas reduce the pressure difference between the gas and gas at the stack and the tour level, right? So which decreases again the ascending energy. So what do I mean? So for example, if you follow the Bernoulli's equation, P1 plus half rho V square plus I guess it is H, right? Or P by, I guess P. Okay, let's check this out. Let's write everything in mass. Okay. So pressure at one point plus half mv square plus you have your mgh, right? Which is constant. Please correct me if I'm wrong. This is energy. This is energy. So force F dot S is your work done, and work done equals to energy. And so what is it? P by H or what? Or it is G? Pressure is nothing but force time area, right? So F equals to P by A. So there is one unit missing, okay? And yeah, so because when you try to, this is your equation, right? So P1 half mv square plus mgh. Now when you try to increase pressure, let's say you have P1, P2, or I can say, It's a pressure is directly proportional to. Oh, is it directly proportional? No, I don't think so. So when you have, yeah, when you have more pressure difference, right? So higher the pressure difference, higher the faster the gas can flow. Right. From here we can see. So again there is the next term called P2 plus half m V2 square. So you can take it at height, right? You can remove that height because yeah, you can keep that height. Okay. Now let's keep it as a constant. Okay. Now, when you try to solve this, so when you P1, so P1 minus P2 will be equals to half m V1 square minus half m V2 square. So it's mostly you can probably see P1 minus P2 taking out some constant is equals to some constant times V1 square minus V2 square. Right. So the higher the pressure difference, the faster your fluid can flow, and the less the pressure difference, the slower it can flow. That's what we use in aeroplane lift also, right? So yeah, and if you maintain top pressure, the whatever the let's say initially the pressure was P1, and from bottom you are trying to purge it at P2. After some time the pressure is, let's say you are trying to increase pressure, you are doing the top pressure, okay, and there is pressure from bottom, it is P2. It is from bottom it is 10, right? Let's say it is as a P3. Then the difference here will be small. That means the velocity with which the gas can move upward will be small. That means you are giving more amount of contact time between your iron ore and the gas, right? The carbon monoxide. So that is about one thing, right? Now, what are the disadvantages? Right, the combustion of the again there are other trends also that has been followed. Instead of using from the tubes, instead of just using carbon dioxide, people are trying to use methane also. So what does this do is this methane will react with your oxygen to give 2 moles of carbon monoxide and hydrogen, 4 moles of hydrogen. These two are highly reducing agents and are good for the indirect reduction, right? Right. So this thing is can be easily you can increase the efficiency by introducing the methane, or you can directly introduce hydrogen, or you can introduce steam. The steam will again break down to give you hydrogen and the carbon monoxide. But this reaction is a cooling reaction. It's an endothermic reaction. So it will cool your at the Tours level. It will cool your blast furnace at the Tours level, right? So again, which is not required. So that's why we do not use the complete steam or this. So that's why we introduce oxygen, but with that we also introduce hydrogen or methane. Right. Again, I have mentioned the steam. If you inject steam, it will give you carbon monoxide and hydrogen, but it again decreases the head temperature because it is highly endothermic. And and we need to preheat your gas, because if you do not preheat your gas, there is a lot of energy will be being wasted there, which will be only being used into converting your temperature of your gas, so which is not efficient. Now see, whenever we are trying to use blast furnace, there are disadvantages. The main disadvantage is you cannot control the composition of pig iron, right, from batch to batch or from tap to tap, right. Tapping is nothing but you take out the liquid metal from the iron, from the heart. So you cannot have good how should I say, the control over the composition. So yeah, and again, high operating and controlling cost. Why? Because the amount that you are using here is very large when compared to other iron production processes, right? So if for example some of the tubes got blocked or choked, so and the region there will become cooled down very fastly, so and it will hinder your final process. So the operating cost is very large, and the coke again that you are trying to use is also very large, right? And not only, see, if you are simply using coke, that's fine, because to form coke there is the different process that has been going on, right? You are taking coal, you are making it into shaft, you're doing the destructive distillation, you are collecting the coke mass, and then you are trying to quench that because you do not want them to burn in air. So from there you get the coke, and then you are using in the blast furnace. So yeah, I mean, there are different disadvantages. And when you try to produce something in bulk, right? For example, in blast furnace, you can produce a lot of pig iron, tons of pig iron. So this production cost will dominate your operating costs, high capital, and everything, right? So yeah, there are many disadvantages with your blast furnace, right? So there are courses taught by different professors, like iron making and steel making technology by Professor Mazmudar, Deepak Mazmudar sir, and and yeah, it's the same NPTEL course. Okay, he is also teaching the same NPTEL course. So there you can learn more about the iron making and steel making technology, right? Okay, so let's move on to the next topic. Let's move on to the alternate routes for the iron extraction, right? Now, alternate routes for iron making. See, there are many processes, but they mostly come down to these two. One is the direct reduced iron, which is all mostly called as a DRI, and the rest is the direct reduction smelting process, right? And also the iron making technology, or the iron making process from the blast furnace, is also called as a reduction smelting process, because you're doing reduction and you're doing smelting. And again, I have explained before what is the difference between smelting and melting. Okay, so I'm not going to explain it again because I have already taught you many times in the direct reduction smelting process. And you can use this as, see, this is DRI and this is DSR, okay? The short forms we call it. Okay. And you can see this DRI process and DSR process has two sub branches. One, you can use the gases, that means the indirect reduction, or you can directly use coke, which is the direct reduction. IDR and DR and IDR, right? So the DR is for, let's just simplify them. DR is for, because we are going to use them again and again. So DR is for direct reduction and IDR is for indirect reduction. So indirect reduction, that means you are using gases. In direct reduction, you are using solids. Okay, now let's move on to how they are being distinguished, right? So DR process will give you solid iron, it will not give you liquid iron. Okay, so direct process produces solid iron mostly with a very little indirect reduction agent. So, and in DSR process, the output is your liquid metal, because I am saying smelting involves melting, right? So you have your hot metal coming from the DSR process. And there are, in DRI process, you can see there are different types of furnaces. Again, the same, the rotary kiln, you have rotating kiln or rotating hearth you can take, or you have shaft furnaces, low shaft furnaces. And shaft is, you know what is the difference, what is shaft? Shaft is nothing but the vertical furnace, right? Vertical tubular furnace. And there are static bed reactors, and there are fluidized bed reactors. Fluidized bed reactors is nothing but, I've explained before, fluidization is nothing but, suppose you have very fine particles and we are making them fluidized. Fluidized is nothing but, fine particles or solid particles, they do not move randomly like liquid particles, right? So you are making them fluidized. That means they appear to be fluid. That means the particles are randomly moving here and there. And the fluidized bed has better the heat transfer and reducibility. Why? Because because whenever the particles are behaving as a fluid, that means each particle is mostly covered by your gas. Okay, so there is a high contact area between your gas and solid, and which is good for reducing and heat transfer, mass transfer, everything. Because whenever you have this, see, when you see in any type of reduction process, at first there are different steps that see, any type of reaction, the rate of reaction depends upon the kinetic parameters, right? And whichever the slowest will define your rate of the reaction. Let's say the rate of the reaction depends upon many parameters. It can be linear proportional, it can be power to something, okay? So proportional, right? So, and whichever is the slowest among this process, right, that is your rate controlling step, because the other things are happening very fast, right? So they are happening in a fraction of seconds. They are not controlling your overall reaction. Which is the slowest step is your rate will be your rate controlling reaction, but because that will define the amount of time it is required, right? At first you will have this huge gaseous layer. Let's say this is my Fe2O3. Okay, so at first the hydrogen will adsorb and will react with Fe2O3 to give me Fe3O4 or FeO or FeO. Okay, FeO or Fe, depending upon what is the present on the surface. Now, whenever these things happen, the carbon monoxide has went into, and the coming out is carbon dioxide, right? So whenever the carbon dioxide comes, there is the concentration gradient. At the surface, the carbon dioxide concentration is high, but at far region, at the further point, the carbon dioxide concentration is very small, right? So that's why there is this concentration gradient, right? And the larger the concentration gradient, the more will be the larger the concentration gradient, the higher will be the flux of carbon dioxide atoms that will be coming from here to here. And if this concentration gradient is very small, then the flux requires more amount of time. That means the movement of these atoms requires large amount of time. So if you can avoid this thing by purging more and more amount of carbon monoxide, that means the concentration you are trying to dip it. That means the concentration gradient is so steep that once the carbon monoxide comes there, it will directly transfer or go away from it. Because the concentration gradient is so steep, the rate of flux will be very fast, right? So that means you are trying to eliminate this gas interface layer, right? So, or you can more technically you can say more technically, how should I say, the concentration layer or the diffusion layer, you are trying to remove that. Once you remove the diffusion layer, that means you are trying to remove this concentration gradient, right? That means if there is no concentration gradient, they can easily jump, the carbon dioxide can easily come out, right? So that is about this. That means in the fluidized bed, that's why we say in fluidized bed reactor there is a very fast mass control rate and very fast heat control, heat transfer, right? So that is more suitable. And again, the DSR, the direct smelting process. In direct smelting process, we do not use coking coal. Okay, we do not use coke. We use non-coking coal as a reducing agent, and that means we are completely avoiding the coking process. Right? So only we need to do is ore preparation. Either you do the pellet or sinter. It depends upon you, which is more economically efficient. Right? If you have very much amount of money, then you can directly go to pelletizing process, right? Because the pelletizing is more engineerily structured when compared to a sinter. And again, I have explained before, pellets have more porosity when compared to your sinters. Right? Sinters mostly happen by fusing. Whenever there is a fusing, there is a less porosity. Okay. And yeah. And again, whenever you are trying non-coking codes, so there is a better material handling, so material less cost, lesser energy, so consume lesser energy because you are not doing any destructive distillation. So yeah, again this DSR process can be installed everywhere, right? It can be installed easily. You no need to have a very big things to do, right? So and then you can get pig iron as usual, same as from blast furnace again, which can be fed directly to the steel melting units. And steel melting units, you have BOF, which is a basic oxygen furnace, or you can go for electric arc furnace. Okay, and in electric arc furnace, you can have this leverage of using how much amount of liquid metal you have to liquid metal or scrap that you can use. You can directly use. You can see the basic advantage of electric arc furnace is you can go up to 90 to 95% of electric scrap. Okay, so 90% of electric scrap. And yeah, it takes energy, but there is no limitation for that. This is the amount you need to use. This is the amount you need to use. Okay, and why? Because yeah, the only thing is you are going to use more, end up with using more amount of energy. Okay, so that's why to get more efficient, I exactly don't know the number. What is the phase fraction or the fraction of hot metal and the fraction of steel scrap that people used in electric arc furnace? So we will discuss this in the extra session. Okay. Now, yeah. So in DSR process is vastly used in world. So when we use gas base is nothing but you are trying to use either you gasify your coke, and that means you burn your coal, you get the reducing gases, and these reducing gases are fed to your furnaces or rotary kilns, whatever we have discussed, with shafts, rotary kilns, rotary hearths, fluidized bed reactors, so on and so forth, right? So whenever you use gas, that means it is called as a gas based DR or DSR process. Okay, so in this you can either use steam, you can either use steam, you can either use methane, okay, or you can use mixture of these guys, or you can use some mixture of oxygen also, right? So you will end up with carbon monoxide plus H2O. Same goes here, you will end up with carbon monoxide plus H2, not H2O, it's H2. I'm not going to balance these reactions, okay? Again, this is my endothermic reaction. Oh, sorry, this is my exothermic reaction, but this is my endothermic reaction. So, yeah, you can. This is an exothermic reaction, right? Sorry, endothermic reaction. You can enhance this reaction by using some catalysts, right? Either you can use nickel or platinum. So if you heat nickel or platinum substrate above 700 degrees centigrade, they can actively help you in breaking your CH4 and H2O reaction. Right. So the gases that we can use can contain your carbon monoxide, hydrogen, steam, and H2O. These are the mixture of gases that you find. Right. Now let's move on to the different process that we see. Okay, so depending upon the shape of the furnace, also there are names given to these things. Okay, again we have discussed before. One is your gas-based reaction, and the other one is your solid-based reaction. That means you are using directly coal, or less up layers or packed bed of coal. Okay, so solid based reaction. Now in gas based reaction you can have gas reforming, that is nothing but you use natural gas, and you use the natural gas, that means the CH4 or some other hydrocarbons, and you break those hydrocarbons into carbon monoxide and hydrogen by reacting with steam. So that is called as a gas reforming, right? And or you can use coal and you do the gasification, that means you burn the coal, right? Gasification of coal. In solid phase reaction, you directly use the coal, okay? Or you take this coal and do the gasification. Right? And while using these two, let's say while using these two, and if your furnace is a shaft furnace, that means it's a vertically cylindrical furnace, okay? So then you have two things coming. One is from this guy. So one is coming from these two, which is the Midrex process. And if we use the gasification of coal and the combination of gasification of coal and shaft furnace, then that is called as a Corex process. There is another process also which is called an underground process, which will come into in a bit. Now, there are first two types. One is what type of reducing agents you are using, either it is gas or solid. The next is the type of furnace. Now, if we use like fluidized bed, there is other type of furnace, fluidized bed, right? And again the same. If I use gas reforming, if I use gasification of coal, if I use gas reforming and fluidized bed, and that is called as a Finmet process. And there are other things also, iron carbide process, Circuit process. There are different names that people give it them. And again, if you use gasification of coal and fluidized bed, then that process is called as your Circuit process. Okay. And if I use directly coal and my rotary hearth as my furnace, then that is called as a Comet process. Comet, Fastmet, the different process. And if I use a rotary kiln, again please remember the difference between the rotary kiln and rotary hearth. Rotary kiln is a horizontal tubular furnace, but it is in an inclined position. It will look like this. We have seen this actually, and this is called as a SL or RN process. Okay. And the rotary kiln will mostly look like this. You charge at one point, you take it out from other point, and this guy will turn. Rotates at certain RPM, not very high speed, but at a certain low RPM. Okay. No. All these are for direct reduction process. Again, the same will carry out for direct smelting direct reduction smelting process also. Then the names will be somewhat different. Okay. So nothing more. Nothing theoretically different things. So the only thing is the type of reducing agent you are using, not agent, or type of reducing matter you are trying to use, like either it is a gas or it is a direct solid, and the type of furnace you are trying to use. So there are two things that define your name in the DRA or DRS process. Okay, though the type of fuel that you are trying to use, whether it is a gas or solid, and the next is the type of furnace you are trying to use, whether it is a rotary kiln or fluidized bed or rotary hearth or and so on, or shaft, right? And in the rotary hearth you have a more what should I say? So it rotates along its center. Okay, so it is not inclined. It is the top right cylindrical furnace, same. But the only thing is the height is small, the diameter will be large. And in shaft furnace, the diameter will be small and the height will be large. So that's it. That's the maximum difference that you will find in this furnace. Everything is same. You use reducing agents, the iron will undergo the reduction, it will form metallic iron. If you are talking about DRA, you will have a solid iron. If you are talking about DRS, you will have a liquid iron. So there is no like technologically very big difference. The only thing is the type of furnace, the type of shaft, the type of furnace, or you can say the shape of the furnace, and the type of reducing agent that you are trying to use, whether it is your solid or liquid. Right, so these are the two differences. Now, so this rotates along again the center axis, but it is horizontally inclined a bit. Okay. So charging is from one side, from the top side, and the loading will be taken from the bottom side, this side. Again, if you use iron source, again here in direct smelting process, the type of ore is also very much important. That means the shape of the ore, either it is a pellet or a lump ore, or it is a fine ore. Okay, fine ore can be used in the fluidized bed, because the smaller the particles size, there is a drop off between the fluidized bed. If you have very large particles, then the fluidization is very much how should I say, is very much difficult. And if you have very fine particles, there will be a lot of dust. So again, that is not suitable. So there is this trade-off between the particle size, not very small, not very large. So let's say we use fine ore, we can use for a fluidized bed. Again, the next thing is the type of furnace and the type of coal you are trying to use, or the energy reducing agent. So if you use electricity, then it will be electrical smelting. And if you are using charge bed, then it is a bed type process. And if you are using bath process, then it is again a different metal slag bath. So that's it. That's the maximum differences. Again, the names will come like Technored, Corex, Finex. So that the DOS, Cyclone. If you use Cyclone type of furnace, then what happens? So yeah, we will not go like deep into that, because there are many. It will take like few lectures to explain every type of furnace, the shapes, the design, and how the charging happens. So which will be covered in iron making technology, where they have where we will have much more time to discuss. There itself we do not discuss everything, because of the time constraint, right? Because mostly you will get like what every week 5 lectures, and even if I take one lecture for one type of furnace, right? So it will take weeks, right? Because in DR process only we have this many type, and for DRS there will be same amount of number. So that is not physically possible unless we are only discussing. We keep an NPTEL lecture for only the direct or the other routes for iron making. Right? So yeah, this is for advanced learning, which is not for our which is not required for us, right? Now, whatever the direct reduced iron that you get from the rotary kiln process, you get a sponge iron. Okay, it's not actually sponge, but because of these gases escaping from your iron or iron ore or a pellet, it will look like your sponge, because sponge has pores, right? So you will find that many pores in your iron lump ore or pellet, whatever you're trying to reduce. Right? So that's why we call it as sponge ore. Now it doesn't mean your whatever the product that is get is soft as sponge. Okay, so please remember that many people have tried mistaken for the hardness. Okay, so yeah, so rotary kiln I have explained before. There is a vertical shaft, not vertical shaft. Sorry, there is this horizontally inclined tubular furnace. Okay, so which rotates about its center axis, and the same goes for rotary hearth process, which we call as a fast met. Again, the same. It's a coal based process. If you are talking about coal based process, then it is a fast met. So and fluidized bed process we have already explained. There are again vertical low shaft furnaces. There are different things. Okay. Now coming to the sponge iron making. So what are the different things that we find? So if I take about rotary kiln, the horizontal one, you feed, what are the other things? You feed iron ore, you feed coal, not coke, please remember, and you feed flux. Okay, and there are different things, because it is continuously rotating. There will be creation of lots and lots amount of dust, because there is always this friction between the particles when they are trying to move, and there will be erosion, and because of this there will be lots and lots of your dust, right? So that again will be collected from here, and you have your cooler, and then you do the magnetic separation, because you get mostly metallic iron, so which is a ferromagnetic, which can be easily separated. Okay, yeah. Again, the preheating of your air should be done, because if you do not do the air preheating, then which it will, how we are going to reduce if you are not going to use air, right? So that's why you blow air at a certain temperature. Okay. Yeah. So so in India we see TDR process, which is Tisco direct reduction, and Sponge Iron India Limited, which we mostly extensively use this process. Okay. So yeah. And the next is the Midrex process. In again the Midrex process, again you get, if you are talking about gas based reaction, so that means you get up with sponge iron, not hot metal. So what we do is we first purge the gasification chamber. That means you have your coal gasification, you have your coal, you purge oxygen, then you do the cleaning, because whenever you try to burn a coal, as we have discussed before, coal contains moisture, sulfur, there are different things that can be found in your coal, right? The silica will not get oxidized or get evaporated. Okay, so that's why you need to do the gas cleaning, followed by the glass cleaning, and then it goes through the gas heater. That means, again, I have said before, you need to preheat. If you don't preheat, the reaction, the head temperature will go down, or the reaction temperature, the active reaction zone will go down. Okay, so then you feed it to the Midrex process, because as I have said before, Midrex is for shaft, right? Where was it? Yeah, here you have using shaft furnace. Shaft furnace means the vertical tube. Here it is, the vertical one. So you feed your ore, right? You feed your ore and you purge gas from bottom, so gas will move up. Again, you will have scrubbers. Scrubbers are nothing but just like the scrubbers we use to clean our utensils. So the same scrubbers are not the same scrubbers actually. So the same thing will be done to clean the gas, and whatever the recycled gas is there, for example, you get the carbon monoxide, that can be again fed, okay, into the reducing gas atmosphere. Okay. Now moving on to our energy on. So energy on process, environ process, or you can call it as a. So this process doesn't need any gasification thing. Okay. So this use steam, and they don't even use catalytics or catalyst. Okay. So they directly purge carbon dioxide and H2O, or you can say methane plus carbon monoxide plus H2O, and this will make sure to produce carbon monoxide. Okay, how? So how this happens, right? That is the question. Now, so before we have seen, whenever you try to purge methane and hydrogen, it is an endothermic process, right? It's not exothermic. So you need to have a high temperature. So either you do use catalyst, or if you don't use catalyst, what you can do is you mix these guys with carbon monoxide. Now what does this actually does? See, we know this reaction very well, as we have discussed before. You will end up with carbon monoxide plus H2. And the same methane can react with your carbon dioxide or carbon monoxide, right, to give carbon monoxide plus H2. This is an exothermic. When you combine this thing, it will become an exothermic process. So there is no the reforming happens here itself. Okay. So that's why when you try to use the carbon monoxide, when you try to use this guy, the carbon dioxide which has been formed on reduction of iron, the pellet or the iron ore that you are trying to use, this will result in the formation of carbon monoxide, and this is highly exothermic, and this exothermic will hamper down this endothermic process. Okay, this will take care of the energy required for the endothermic process. Aluminum fluoride. So I mean, let's not go into that. Right. And again, most stable metal halides like uranium, titanium, beryllium, zirconium, They can be reduced with your rare, sorry, not rare, the alkali earth metals or alkali metals, right? So they can be reduced with, for example, it can be reduced by zinc, right? So, sorry, not zinc, can be reduced by magnesium. The best example is reduction of your uranium fluoride with magnesium to give magnesium fluoride and uranium. Now, and again, in fluorides also, just like in oxides, there are different types of suboxides also is there. So, or suboxides, higher oxides. So, same goes for fluorides also. There are higher fluorides, subfluorides are there. So, these fluorides again can be reduced with hydrogen or any, not hydrogen, some with other elements also. Or you can, some may be reduced. For example, iron, niobium, aluminum halides can be reduced with hydrogen. Okay. Yeah. So again, if you want to, again, as I've said before, the halides are volatile, highly volatile. That means you can do the fractional distillation. Okay. So fractional distillation is nothing but you maintain some melting points, some range of temperature such that the higher melting point will melt first or condense first rather than the lower melting point. So yeah. So in the halogenation, what we try to do is either you do the halogenation of oxides, right? So you just heat it in presence of either oxygen. Simply heating, roasting will not give you halides. So you need to use some reducing agents with them also. So for example, if you have metal chloride or metal fluoride, it can react. It cannot react with your carbon and give you metal plus CCl4. Okay, this is not possible. So you need to use, let's say, carbon monoxide, or you, if you want to convert them into oxides, right? Which is, it is not possible if you want to convert them into oxides. So you or if you want to convert them into oxides, you cannot just directly do this. No, this is highly unlikely. This reaction doesn't form very much easily, and not just chlorine. There can be chlorine oxides that can also be formed, which is very much poisonous and toxic. So, or you can end up with chlorides, sub oxychlorides. Okay, metal oxychlorides again, which is not feasible. So instead of doing all these things, we go with these things. We go with the other reducing agents. So what these reducing agents do, they give away the oxygen, or they take away the oxygen, and you will form an oxides, right? For example, let's see this reaction, okay? Or for example, if you want to form magnesium chloride, okay? So some reactions may not be directly straightforward. So for example, if I have an oxide and if I want to form chloride, this reaction is not feasible. This reaction, it's not that straightforward. Instead of that, you should use some reducing agent. This will take away this oxygen, and you are remained with MgCl2. This is how things actually happen. So that is about that formation of metal chlorides. Okay. Now let's move on to the how do you get titanium. Titanium is very much important. So let's move on to the titanium part. Yeah. So production or purification of your titanium. Now, whenever you are trying to do the titanium ilmenite, so the best possible ore of your titanium is ilmenite, but ilmenite contains iron, so you do not want iron with you, right? So for that, what we do, we take rutile. So rutile is nothing but either you get a synthetic one, or you do the enrichment process, different types of enrichment process, remove iron as much as possible, or you can use the natural one. Okay. So if you take the natural one, it contains different impurities. So what we do, we first, again the same thing we are trying to do. This is the same thing. So we are trying to add reducing agent such that it will strip the oxygen, and this chlorine will be reacted with your metal. And the same thing we do here. So first we take coke, we mix it with our rutile, and then we do the briquetting or pelletization depending upon the type of furnace and type of thing you are trying to follow. Right, so then we dry it and then we break it onto the different sizes that we want, and then we do the fluidization with the chlorine. Now you are trying to involve the chlorine because our goal is to form chlorides, right? So now you are adding chlorine into the reaction, and this chlorine will react with your briquettes or the TiO2. That will result in the formation of carbon monoxide and chlorine, right? And it happens mostly at 800 to 850 degrees centigrade. Okay, so here you do fluidization. And because again we have said highly volatile, so you will end up gases, right? So dedusting, you will have titanium chloride, right? And what are the other things that you get? You will end up with rutile, the left one, the coke that is reacted and left, and there is the dust also, right? You will have TiCl4, and then you do the condensation. What do? We do the condensation. So how the condensation, and because as I've said before, chlorides have different melting points, and when we try to do the fractional distillation, that means, so for example, A has 400 degrees centigrade as its volatile or the boiling point, B has 350 degrees centigrade. So our mixture is at 500 degrees centigrade. Okay, now what we try to do is we try to cool it till 400 or I should say 390 degrees centigrade. What happens? This guy will turn into your liquid, but not this guy, because 390 is above 350, right? So that means he is still in a vapor form, but the 400 degrees centigrade guy will turn into liquid. That means you are separating liquid and gas. That is easy, separating liquid and gas, right? So that's how you separate, and the same goes for the condensation up to 200 degrees centigrade. When you do that, the FeCl3 will come out. Because I have said before, whenever you are trying to do the extraction of titanium, you have iron with it. So you need to remove iron first. And when you do the scrubbing, and again you add your liquid. Now what I am trying to do, I am trying to add liquid TiCl4, titanium tetrachloride. So because of this, we add this, and we do the scrubbing. Then let's add the scrubbing. The output or the byproducts will be again whatever the remaining FeCl3 is there, that will also come out along with AlCl3. Right, and whatever and again, not only you will have iron, chlorine, you will even have the vanadium also. So vanadium, you will have not only vanadium chloride, as I have said before, when you try to do this, you will end up with magnesium oxochlorides, right? So the same goes for, you will have vanadium oxochloride here. So what we are trying to do, we are trying to reduce right. So whatever the vanadium pentachloride is there, oh sorry, not vanadium pentachloride, oxychloride, right? So that will get reduced, and the bright product will be vanadium trichloride and steam. And what is our introduction? The introduction is H2S, hydrogen sulfide. Right? And then finally, again you do the fractional distillation to separate the sulfur, the fractional distillation. Again you will have sulfur, whatever the remaining H2S, and whatever remaining silicon chloride, and also remaining vanadium chloride. All these things will be taken out, and finally you will have pure titanium tetrachloride. and then this titanium tetrachloride. See the reduction, the getting pure titanium from your alloy is a very complex process, and it takes a huge amount of time. For example, in blast furnace you can do get tons of pig iron in a day or in few hours, but for titanium, which is not possible, because of all these processes, it will take a minimum of like 10 days. So, so for example, you per ton it can take 1 day, more than 1 day. Right? So for 10 tons, if you want to get, you have to work for 10 days. Right? So that's why the pure titanium also is very costly also. Right? And that's the feud between the Russia and this America. So when there is a story for the Blackbird, the SR-71. So and the SR-71 flies about more than Mach 3. We all know that, right? And it is not operational right now. I mean, we are not certain that thing. America military has declared that it is not operational, and the SR-71 is a spy plane. Okay, so it was made in like 70s or 80s to spy Russian regions. Okay, Russian military regions. So and its nickname came known as a Blackbird or SR-71 or 72, right, depending upon the design. Okay. So for them, America needed, and yeah, when you are moving at Mach 3, and even though it's not like space. In space, okay, you can say there is no air friction. So, but to handle those temperatures, you need very strong and steady alloys, the titanium-based alloys, right? So, and the sole producer of the titanium-based alloys during that time was Russia. Okay, so the Americans have to make a deal with them depending upon the aircraft designs. So Russian engineers came to America to know the designs, and American engineers were mostly like made a trade to get these alloys, titanium-based alloys, okay, to build their aircrafts. So that's a very long back story of the Cold War. So yeah, let's not again go into that. And this titanium chloride will be reduced by using magnesium. Okay, and if you are using magnesium, then that is a Kroll's process. Okay, and if you are using sodium, then that is a different process. So I just the scientists' names which people used to produce the titanium. So what they try to do is they mix with the magnesium, and this will result in titanium plus magnesium chloride. Sorry. Okay, so this is what happens. Again, the titanium chloride should be stored in a very tight atmospheres, presence of argon, or because it can easily hydrolyze. And yeah, there is this other thing, good property of this metal halides is that they can be easily hydrolyzed. For example, iron chloride can be dissolved. Iron chloride cannot be dissolved. The rare earth chlorides are easily dissolved in water. They can be easily hydrolyzed and create to give hydrochloric acid. And hydroxides and hydrochloric acid. So that thing is very common in the chlorides family. Okay, and this titanium also has very peculiar property with iron, because see, when you are trying to get titanium, you end up with iron also, because they are very close relation. So that's why you get rutile, not ilmenite, as FeTiO, right? So yeah, and this titanium at certain temperature will form a eutectic mixture with iron. So you need to make sure that you are not reaching that temperature, such that the titanium will stick to your steel balls, and it will react and form the titanium iron alloy. Right? So that is also very much important when you are trying to do extraction of titanium. Okay. Okay. So yeah. In Kroll's process, what we do, we use magnesium as a reducing agent rather than sodium, and so if you use sodium, that process is called as a Hunter's process. So one is Kroll's process, one is the Hunter's process, and in Kroll's process we use magnesium as a reducing agent. And for why the magnesium is more efficient, because the temperature range where we can play. See, there is this gap between melting point and boiling point. because we are using liquid metal, so in this region you have magnesium as liquid. Above this region, the magnesium as vapor, and the vapor-vapor reaction is a bit tricky and not much efficient when compared to the liquid gas interaction. Okay, so yeah, and because of the density difference also the mixing is very much complicated. Okay, so but for sodium this range is very small. Okay, so this melting point to boiling point region is very small, so that's why people trying to avoid this guy and use Crow's process than the Hunter's process. Okay, so people are not using calcium. Calcium can be used, but people are not using calcium because it again forms same. It has much narrower region than this guy, sodium chloride, and also the calcium can form oxychlorides. So again, which is not feasible for us. And yeah, the temperature should not be greater than 1085 degrees centigrade. Above this, you will end up with titanium iron mixture. So people try to avoid this. So that's why there needs to be a good control of the temperature and your atmosphere. If you have even little bit of moisture, that will react and form the chlorides will form hydrolysis and gives the HCl vapors. Okay, so yeah, so that's why there should be a strict control of your injection of a magnesium and also the temperature of the reaction atmosphere, right? So that's that about Crow's process. Now, see, zirconium hafnium can be extracted from a single ore, that is called a zircon sand, because that is a mixture of zircon hafnium. It's a silicate. It's basically a silicate. That means zircon hafnium silicate. So again, to do that, we need to convert them first into your chlorides. So what do? We do again fluidization. We convert them, and we do the fractional distillation, or then you separate whatever. See, so at first you have zirconia sand, right? Zirconia sand contains zirconium hafnium silicate, right? So you do the chlorination, that means you fluidization plus fractional distillation, which will result in the formation of you will get zirconium chloride and hafnium chloride. So, and you have your carbon monoxide, silica tetrachloride, and carbon dioxide. There are two ways from here. Either you do the solvent extraction, SX process, or you do the again chloride distillation. So either way you end up separating the zirconium. If you do this, you will get zirconium oxide. Again, you need to convert them into zirconium chloride. And if you do this, you directly get zirconium chloride. Right? And again, the same process will follow. You use zirconium chloride, you add magnesium, you will get magnesium chloride and zirconium sponge. See, in titanium also, finally you will get titanium sponge, and there you do the crushing and vacuum arc melting to get the ingots, right? So same goes here also. This is for zirconium. And what about the other half part where you separate a hafnium? Same, you take the hafnium, either you do the solvent extraction or you do the chloride distillation, you will have a hafnium chloride. And from hafnium chloride you can go again two ways. Either you can go same, the magnesium one, or you can do the molten salt electrolysis. So if you do the magnesium part, you will end up with sponge, and if you do the molten salt electrolysis, you will end up with crystals. That's it. There is no extra thing. Okay, and finally you will have refining. So you do with the iodide process or electron beam melting. Okay, so yeah, then you will get hafnium alloy ingot. And electrolysis of magnesium chloride is a bit difficult. It's not efficient. So what we do is, instead of doing this magnesium chloride electrolysis, what people are trying to do is you just react it with steam, okay, or you react it with oxygen to give magnesium oxide. And again, this magnesium oxide can be undergo thermal reduction, okay. So thermal reduction, that means you use some metals to reduce magnesium oxide, and it will turn into magnesium. Again, you react it with chlorine to get sorry, again you use this magnesium to reduce titanium tetrachloride, okay. Yeah, so instead of electrolysis, one you can do this thing. The next one is the uranium process or the uranium extraction. The uranium extraction is available as ammonium uranium oxide, okay. So to remove that ammonia, you do the calcination, right? So this is how you see that guy, okay. You will have NH4 taken twice, U2, O7. And the most of the uranium you get from the ore is U238, and U238 is not very much, it's not enriched when compared to U235. So people, there are different technologies to do that, and most reactors, nuclear reactors that we use are U235, right? So weapons grade has more amount of U235 when compared to U238 by 8%, and the reactors, depending upon the type of reactors. For example, the most famous one that do not use enriched uranium is the RBMK reactor, and the RBMK are the scientist names of the Russian scientists who invented that, designed that reactor. Okay, there they don't use the enriched fuel; they directly use U238 because it's cheap, right? You do not have to enrich, right? So they directly use U238 there. And to increase this nuclear neutron, see, whenever you have uranium atom, one neutron bombards and it will undergo fission, so they disintegrate into more two atoms, right? So each neutron either can give 2 or it can give you uh, one neutron. So this is more on probability. So when you do the averaging, it will finally end up with 1.5. Okay, so each neutron when hits your uranium atom, it can produce half a neutron. So now when you don't have enriched uranium, this probability of half getting will be reduced. So to do that, we use enhancement, the nuclear neutrons enhancement things, just like the graphite. So graphite will increase the reaction, this fission reaction, but the control rods will decrease the reaction. So that's how the balancing happens in this RBMK reactor. Okay, let's not go deep into that. So it's simply just for information that RBMK reactors used a direct U238 rather than your U235. And how do you like separate U235? So all you need to do is first you convert everything into fluoride forms, right? And these fluorides are UF6, uranium hexafluoride, is then put in a drum and rotated for 90,000 rotations per minute. Because of the centrifugal force, the U238 will go away to the periphery, U235 will be remain at the center. So that's how you do the enrichment process. Okay, and this can be used in your directly used in whether in a weapon grade or in your reactor grade, depending upon the type of grade that you are expecting. Now coming to that, you do the calcination. When you do the calcination, you end up with uranium trioxide, ammonia, and steel. And this is again, the higher oxides or higher fluorides can be reduced with hydrogen to give lower oxides, right? Steel. And this uranium oxide is again we finally have to get fluorides, right? Is reacted with hydrogen fluoride to get uranium tetrafluoride plus steel. Okay, and either you directly reduce with calcium to get CaF2 and uranium liquid, or you want to increase the fluoride number. So again, you react it with fluorine, you get UF6. Okay. So this UF6 is taken into the rotating drums, and they are rotated at very high speed to enrich U235 and U238. That's it. So that's about uh, the halide metallurgy, right? Now coming to the chemical refining. See, the chemical refining is a final step in your metal refining or metal extraction process. Okay, metal extraction process. So let's move on to the refining process. See, there is this from statistical people who are familiar with metallurgy, they can relate this. In statistical metallurgy or statistical entropy, not metallurgy. In statistical, when you try to prove the statistical entropy, so you will end up with this relation: delta x equals to xa ln xa plus xb ln xb. Okay, this minus xa ln xb. And what are these? This is mole fraction of A atoms and mole fraction of B atoms. And what is delta G? Delta G, let's say this is an ideal solution. Ideal solution is nothing but the entropy, the enthalpy of mixing. That means when you mix A element and B element. That means, for example, you are making an alloy, iron and nickel alloy, for example, iron or steel, chromium alloy, iron silicon alloy. And let's say the Xb is your impurity. Okay, so that means when you mix two things, the total enthalpy is not changing; it's remaining as zero. Okay, there is no heat energy released or heat energy absorbed. So yeah, that means the delta H is zero. That means the only thing that remains is T delta S. Now if I differentiate dou delta G by dou T or dt, and this not dt. Okay, so let's temperature. Let's differentiate it the mole fraction. Okay, so if I do this, dGA by dXA will result in XA will go out. So that means first you will have ln XA minus 1, and if I do the same for this guy, then I will end up with, you can write XB as 1 minus XA. Okay, and you do the differentiation, then I will remain with minus ln XB plus 1. This 1 will go away. You will end up with ln XA minus ln XB. And that means if you want to have very pure metal, that means the XB should be tending to 0 and XA should be tending to 1. And if you apply a limit XA tending to 0 or XB tending to 0, this guy will be 0. And this will turn out to be a minus infinite. That means the slope will be minus infinite. So that means the free energy will shoot up upwards. That means the free energy will be moving into positive region. Minus negative, right? So this is how the slope looks like. That means the free energy required to make a pure metal will shoots up as you decrease the mole fraction of other impurities. That means the system wants to have some impurities into the solution so that it can decrease its free energy. And this we have discussed before. If any system wants to attain a normal equilibrium state, that means the equilibrium state must have a minimum free energy, right? Or the stable phase for a system to attain. That means that state should have minimum free energy. And if you have a maximum positive free energy, then that system tries to have maintain a minimum free energy. So that's how the system will take up impurities and minimize its free energy. Okay, so that's why the more the pure the metal it is, the higher will be the cost. Why? Because you need to use tremendous amount of energy to purify any metal to its purest form. So that's why there is this grades that are given. For example, if you take copper, there are these 9 grades. Okay, so 1 9, 2 9s, 3 9s, 4 9s. What is the value of 5 9 grade, 6 9 grade, 7 9 grade? What does that mean? That means the 99.9, 1 9, and 2 9 means 99.2 9s. 3 nines, 4 nines, 5 nines, and for like the highest purity of copper that used for this electrical purposes is 5 nines, and that's why the copper that comes is very costly, you know. So there are 5 9 grades. There are companies that use 5 9 grades, 4 9 grades copper to produce the wires, okay, copper wires. So that's why these wires are very costly. Right? And the lower the impurity, the higher will be the current carrying conduction. The conductivity will be very high. So higher the impurities, the conductivity will drop. So that's how the purity defines your cost. Okay, and the common metals that undergoes the physical and chemical characteristics refined based on difference in physical and chemical characteristics are copper, lead, zinc, nickel, tin, aluminum. So there are different ways you can do the refining process. The first one is either you do the selective oxidation, okay, that is one way of doing. Right. So let's write that thing. Now, how do you define? One is the chemical refining. In chemical refining, I do the selective reduction, or you can call it the selective oxidation. In selective oxidation, you selectively oxidize impurities, and they leave as a slag, and you take out the molten metal. Or you can do the precipitation from the melt. Now, how the precipitation to melts happen? So impurities in your molten metal can be precipitate out. Now, how do you do the precipitate out? Either you do the dross formation again. Either you form the dross or you form the matte. We know what is matte. Matte is a liquid molten sulfides or molten sulfides. It's a mixture of molten sulfides. That means it is happening by adding sulfur. Okay, you add the sulfur, you form the sulfides, and you take it out from the metal because sulfides have less density. What about dross? Dross is a heterogeneous mixture of metals and metal oxides or metal sulfides also. It is not a like maximum mixture of. In matte you will find more than 90% of molten sulfides. In slag you will find mostly oxides with minutes of sulfides and this. And in species you find the antimons, bismuths, so antimonides, right? But in dross it is a heterogeneous mixture of solid or metal and metal oxide. So it contains both metal and metal oxides, and it is not completely fluid as your matte or slags. It is mostly solid or semi-solid. So that's why you dross that we get is mostly a solid or semi-solid type or paste type. Okay, and how it happens? Because when for example mostly the alumina dross we talk about, the dross that mostly come from is alumina drosses. So in alumina drosses you have alumina and some amount of pure aluminum being trapped in that alumina. Okay, on your aluminum solid particles, some of the aluminum will be trapped as a liquid onto the alumina species. The alumina solid particles. Okay, so that's why it appears as a paste, not as a solid or not as a liquid. Some processes are some processes are maybe taken as solids. So that is one thing. Yeah, the molten metal and one or more of the impurity dissolved therein, or a foreign metal intentionally added and the impurity in the metal in the molten bar. So that's how we do it. Or the next one is the chemical transport. So how do we do it? The next one is the chemical transport. No, the metal is selectively converted into. In chemical transport is nothing but you are trying to take one compound from other, right? You are moving something, and moving is nothing but something needs to be volatile or something needs to be liquid and separated, right? So to form the volatile things, you need to react to the impurities with certain metals or gas phases such that they convert into the volatile gas phase. So for example, you do carbonyl process in the process of refining nickel, right? So nickel will be taken as reacting with carbonyl, carbon monoxide, to give nickel carbonyls, and again that can be decomposed to get nickel liquid. So yeah, that is the chemical transport, and yeah, that is the volatile or the transport. And the next one is, these are all come under chemical refining. Selective oxidation, precipitation from melt, chemical transport, they all come under chemical refining. And the next one is the physical refining. The physical refining is you use the physical characteristics. For example, we use vacuum to remove the impurities. For example, gaseous phases, the oxygen remained in melt, or carbon that is remained in melt. So that is one. Or the zone melting, mostly done for the semiconductors. The basic theory behind the zone melting is, at higher temperature, impurities should dissolve. Okay, so yeah, that is the zone refining. And the next one is the electric arc melting and vacuum distillation. And the last one is electro refining. Electro refining is mostly like you have an anode, impure anode, you have a pure cathode, and anode means you are trying to in electro refining, what we do is, in anode we dissolve whatever the chemical elements are. Let's take an example of a copper. You take the copper that you got from converting process, you make it in sheets. Now what you try to do is, you take that impure copper as an anode and you take a pure copper as a cathode. Now you apply electricity. In electro refining we use electricity to convert electric energy into chemical energy. So this copper will get dissolved and will come, so at anode, anox red cat, please remember this. And whatever the process, either it is electrolytic or electro refining or anything, at anode only oxidation happens. Okay, either you are giving electrical energy or you are taking the electrical energy. Okay. So at anode only oxidation happens. So anox, red cat, that means reduction happens at cathode. So at anode, the oxidation, that means the copper what is present in elemental form will undergo oxidation and become ions, and they travel and they deposit at cathode, where they undergo reduction. Ions are converting into the copper form, and whatever the impurities will be left as a slime at the bottom. That's all about the electro refining. Electro refining is good. Mostly we use it for copper refining thing. Okay. And the best example for the selective oxidation is your BOF, basic oxygen furnace. So BOF handles at 1500 degree to 1600 degree centigrade. At that you will have a molten metal. You purge oxygen through lamps at Mach speeds, or supersonic, not even above Mach speed. Okay, at supersonic speeds, and this oxygen will stir, agitate, and everything will happen. And we will not discuss this because the time is also running out, and it is very advanced process. So you use that oxygen where the iron will also get oxidized, but mostly the impurities will get oxidized, and they will be picked up by slag, where we add calcium oxide. So this calcium oxide will pick up the silica, the manganese oxide, the phosphorus pentoxide, many things will be picked up. So yeah, that's about this selective oxidation. And for copper refining, we do the preliminary refining, where we do the fire refining. That means the fire refining is done. So in here we remove the fire refining. That means we are supplying oxygen. So oxygen to remove sulfur. Whatever the sulfur is still present in your copper, blister copper. So blister copper contains sulfur. So sulfur is being reduced by oxygen, where we purge oxygen. Oxygen will react with sulfur, give sulfur oxide, and some of the impurities also will get oxidized. So like aluminium, silicon, manganese, zinc, tin, many elements will get oxidized, and they will be picked up by slag. And some of the copper will also get oxidized, but again we maintain some reducing atmospheres. We do the deoxidation to get copper oxide, okay. And then we do the electro refining, just electrolytic refining. As I have said before, you take impure anode and then you take pure cathode, and you apply some electrical energy, and these copper ions will travel from here to anode to cathode, and the impurities will be remain at the bottom. So they can be called as slimes. Okay, and finally final refining. mm, and again they are melted into electric arc furnace, and they are get into certain ingots or shapes. So yeah, and also we use the carbon. So or you can say the fire woods, which is coated with your carbon, and then we melt it, same again the same process we did in the fire refinery, which is happening here. Okay, so that is about the copper refining. Yeah, coming to the selective oxidation. Yeah, so the copper is melting then compressed. See, this happens, right? The copper in refining converting process where you do the sulfidation roasting. So copper sulfide will react with copper oxide to give copper and sulfur dioxide. And with impurity metals, the copper oxide will be reduced to get copper. And yeah, and deoxidation you use in two ways, whether by poling or gaseous reduction. Poling is nothing but you add wood. Wood is mostly made up of carbon, and carbon will reduce whatever the impurities are present in it. And gaseous, again the same, methane, ethane or higher hydrocarbons to remove our impurities. Okay, that is about fire refining. And selective oxidation, again you maintain certain partial pressures of oxidation environment such that certain will get oxidized, certain elements will not get oxidized. So this is done for gold bullion, Miller's process. So to remove the impurities and to get the final gold. And the same goes for silver also. Okay, so yeah, that is all about for today's session. We will discuss the remaining in the next session. Also we'll discuss some few problems. Okay, so thank you for joining today's session. In the next session also we'll discuss some few problems. Okay, so thank you for joining today's session.